Hello, everyone. Good to see you. Today we have Guglielmo Nocera from IHS, who's going to talk to us about assembly maps in topology. Thank
Thank you very much. Thank you so much for the opportunity to speak. And okay, so as announced, I will not start with a definition, but with a conjecture. And this is known as the Kaplansky conjecture. So what I will do in the first half an hour, ideally, of this talk is to try to explain a principle. And there will be two instances of this principle. And after that, I hope the principle will be somehow motivated enough. And I will move to a third one, which is the one I'm working on, which is the so-called Farrell-Jones conjecture. But I will start with two simpler ones. So the first is around this Kaplansky conjecture, which is very, very elementary. So suppose you have a torsion-free group, and this may be any torsion-free group, like even non-commutative. We're not talking about topological groups. We're only talking about discrete groups um, for the whole talk, actually. And let F be a field of characteristic 0. Then 0 and 1 are the only idempotents in F of G, the group ring. Okay, this is not uh, proven, and it's a conjecture. Um, let's say that if G is not torsion free and you have an element of finite order, you can build idempotent elements in a standard way. But if you somehow cut out that phenomenon, you suppose your group is torsion free, then it's harder to think about idempotent elements in the group ring. And so the conjecture is even that 0 and 1 are the only ones. I will not talk about how to tackle this conjecture. I will rather give a criterion to imply this conjecture. And this criterion uses the formalism of K-theory in a very, very easy way. And then we'll move forward in this direction. So let me recall something you all probably know, which is the definition of the K0 of a ring. So suppose R is a ring. The projective class group of R, denoted as K0 of R, also known as a Grothendieck group, is the abelian group like defined as generators, generators are isomorphism classes P of finitely generated projective R modules. And relations are generated by the following, actually. So P0 plus P2 is equal to P1 if there exists a short exit sequence 0, P0, P1, P2. Notice that I didn't say a commutative ring. Of course, in the case of commutative rings, it's easier to think about modules because you don't have to pay attention to left and right. But in fact, this also makes sense for non-commutative rings. And yeah, and it's not like a pathological area of the world. It's really something you want to think about. And you can also define the reduced K0, so reduced projective class group. This is just like in homology, you quotient by a copy of something related to the integers. So it's actually defined as the co-kernel of a natural map between K0 of Z and K0 of R. And this map arises from the natural map from Z to R, but it can also be interpreted as quotienting K0 of R by the free modules. So inside the projective ones. Free R modules, of course. Okay, how is this related to the conjecture? Well, there is a conjecture, which, spoiler, implies the first one, that if G is torsion-free, then the reduced K0 of the group ring with coefficients in Z, I usually drop the brackets, but when I write RG, I mean R of G, is 0. And for every field of characteristic 0, K0 reduced of FG is 0 as well. Okay? And the point is that theorem, let me write this and I'll explain it. This implies the Kaplansky conjecture. So when I say implies, I always receive this question, so let me make this clear. I mean that if you have a torsion-free group and its reduced K0 with coefficient in Z vanishes, and also for every field this vanishes, then for every field of characteristic 0, 0 and 1 are the only idempotents in FG. So the state, the conclusion of the second conjecture implies the conclusion of the first conjecture. This is what I mean by imply. So basically, if you prove the first one, then automatically you have, the second one, you automatically have the Kaplansky conjecture. Okay, so this is just the first example of something in K-theory implying something else, which in principle one is going to have something to do with K1. There's
So we lost your screen
yes.
for
I
a
saw.
second here.
Let me see if I can reconnect. Okay. And now via Zoom.
Yes, great. We can see.
It's a good way to break. Okay. So definition, R ring, then K1 of R is the abelian group where generators are conjugacy classes F of automorphisms F from P to P, where P is, as above, a finitely generated projective R module. And relations are generated by the following two. So one is the unavoidable one. G composed F is equal to the sum. And the other one is exactly the same as above, like F0 plus F2 is equal to F1. If I say if because the relations generate the actual relations. So if there exists a short exact sequence, let me write it like this, and F0, F1, F2. Okay, so you're already given P0, P1, P2. you're asking that there are such maps here, which make this into a short exec sequence, and adding these automorphisms makes everything commute. Okay. Definition, the weighted group of G is defined as the quotient of this K1 of ZG mod this, let me say, primitive elements. So these embed naturally into K1 as if you want automorphisms of the free ring, the ZG module of dimension 1. If, yeah, that's a way to see them. And okay, so it makes sense to quotient by those. And this is a weighted group. Okay, so now that we have hopefully a good grasp on K1, let's go in the direction of formulating a conjecture that will be tackled by using K1. Okay, so we're trying to reproduce what happened at the level of K0. Let's M be an n topological manifold. Okay, and so yeah, something locally homeomorphic to Rn. An H cobordism over M is an n+1 manifold W with boundary. So when I say manifold, I always mean without boundary. So M is without boundary, such that the boundary of W is decomposes into two pieces. One is M, and the other one is another n manifold, and topological manifold. I'll never talk about smooth manifolds in this talk. And also the two embeddings, M inside W and N inside W, are both homotopy equivalences. And for this reason, the H. We denote by H of M the set, this is just a set for us, of H cobordisms over M, quotiented by the relation of being homeomorphic rel M, which means M is embedded in, say, two different cobordisms, and I want to exhibit a homeomorphism such that this commutes. So it's relative to M, it's the identity on M. Okay, so this is a way of looking at parameterizing n's, so other manifolds, which are homotopy equivalent to M. It's not the only way, but it goes in that direction, right? So you're in particular, M and N are homotopy equivalent, and they are by means of a bigger manifold somehow. Theorem as cobordism theorem. If M is a closed manifold, so no boundary and compact, of dimension greater or equal than 5, then there is a bijection between the set of H cobordisms over M, which I want to underline somehow is a set of manifolds which are homotopy equivalent to M, in roughly speaking, and our weighted group of the fundamental group of M. So in particular, this tells you that these H cobordisms really have to do with the fundamental group of the manifold, not with this whole weak homotopy type. But, spoiler, we will be restricting ourselves to spherical manifolds. So manifolds whose higher homotopy groups vanish. And this is one reason why this theorem will be so important to us. Like, okay, we're speaking of a way to parameterize other manifolds which are homotopy equivalent to the first one, but this cannot be all of them, right? Because otherwise the pi1 would somehow characterize the whole weak homotopy type. Okay, it's not the case, but it's the case in the aspherical setting. I hope this disclaimer is clear, but otherwise don't worry. I mean, it's not, it's just heuristics. So consequence, if y of G is trivial, then actually it's an if and only if. For every closed manifold,
Hey, I think we lost your
okay, sorry, I'm
screen
back.
again.
I don't know why this happens. Probably there's some connection faults, but now you should be seeing again.
Yes, we do.
Okay,
Perfect.
sorry. Okay, so I just wanted to say that a very easy consequence of this is that if you fix your group, then for every closed manifold of high dimension, whose fundamental group is isomorphic to G, then every H cobordism over M is trivial. Trivial meaning that it's homeomorphic to 0, 1 times M. And in particular, this means that every N which is obtained this way will be not only homotopy equivalent to M, but homeomorphic. And this is the big consequence. We're somehow saying something along the lines, if N is homotopy equivalent to M, then it's actually homeomorphic. Okay. Provided they have this, sorry, it's homotopy equivalent via an H cobordism. We're only speaking about the specific case. Okay. And let me close this long introduction by stating the big conjecture. So a closed manifold N is called topologically rigid if any homotopy equivalence from M to N whose source, so with another closed manifold M as a source, is, let me call this F, is homotopic to a homomorphism. So in short, N is rigid, is topologically rigid, is if any add other manifold which is homotopy equivalent to it is actually homomorphic to it. But you have to require compactness, because otherwise you may have something like this. This is, of course, a homotopy equivalence. It's not a homeomorphism. It's not even homotopic to homomorphism. This would be S1. But the trick is that either you see this with boundary and it's not a closed manifold, or you see it without boundary and it's not a closed manifold because it's not compact. So you're excluding this phenomenon. So conjecture, the Gbia group, an aspherical manifold. So let me recall, aspherical means pi I of M is 0 for any I different than 1. Let me say different and not bigger so that we also have connected. Okay, with such that pi1 of m is isomorphic to G is topologically rigid. So this is a very ambitious statement because you're saying that for any possible group, this is true. And the maybe surprising thing is that there's no counterexample known to anyone, as far as I know. So yeah, if usually if you try to come up with an example, you get this kind of situation, which is not allowed. So yeah, it's not true. I mean, sorry, there's no counterexample. And okay. And now I want to move to the Farrell-Jones conjecture, which is a K-theoretic criterion again that implies the Borel conjecture. So you will try to prove something in K-theory and also L-theory. And if you're successful, then you have the Borel conjecture. Sorry, this is called the Borel conjecture for free. Okay, so this is really the central statement of this talk. Our efforts will be going in the direction of having some tool to prove this. Maybe I can just say that we'll actually say this again, but in low dimensions, the Borel conjecture follows from classification results. So dimension 1 and 2, this is classification of curves and surfaces. In dimension 3, it's much more complicated and interesting. It does follow from Perelman's proof of Thurston's geometrization conjecture, which is easily one of the most important results in geometric topology. Conjecture. In dimension 4, I mean, it shouldn't surprise anyone. There's a big question mark. And we are going to see something relative to dimension greater or equal than 5 in a moment. So goodbye low dimensions for this talk. So let me say we're going to talk about the Farrell-Jones conjecture. For those of you who never heard of K-theory or are not familiar with, let me recall the fact that there actually are higher K groups, Kn of R, for every, actually for every n in Z, and also reduced K groups. And they actually form a spectrum. For those of you who don't know what a spectrum is, but I guess almost all of you do, or probably all of you do, never mind, but so in particular, they are tied to a homology theory. So they correspond to a homology theory, which I will call KR. So this is a spectrum. And we will be interested in things of the form K of RG. So, I mean, I will switch between these two notations in the sense that this will usually be coefficients for some other homology theory, but I'll get there. Okay, so two very simple properties. Well, the first one is not very simple, but these are clues to something else, are the following. Kn of Rz, so this is the group ring, well, for the group Z with coefficients in R, and R here is a regular ring, is actually isomorphic, so it splits as Kn of R plus Kn minus 1 of R. If R is not regular, this is not true, and there are other terms. I will get back to them later. And this is known as the fundamental theorem of K-theory. I don't know why. The second property is that reduced K-theory of R, G0, G1, so this is the free product, and suppose these two are torsion-free, and R is regular again, this also splits as this, RG0, RG0 plus Kn reduced of RG1. So why am I recalling these facts? Because one can observe that this is also true for homology in a certain sense, in the following sense. So if H star is any generalized homology theory, then we actually have the following. Hn of Bz is two copies of Hn of the point, shifted. This is just the homology of the sphere, of the one sphere. And you can also see that by how the classifying space of a free product is done, is how it works. You also have the splitting in the same fashion as the splitting in K-theory BG2, we've been talking about before. This is reduced homology. So this is a very, I don't know, heuristic suggestion of something. So the question now is, can we find a generalized homology theory? Let me denote it non-standardly with HR. Generalized homology theory such that HR of a classifying space of a group is actually the K-theory of the ring group, the group ring, sorry. Okay, and this is somehow motivated by the analogy we remarked before. And the very first observation is that since we obviously want something like HRN of the point be equal to Kn of R, so like the trivial group in some sense, zero group, the only candidate, so the reasonable candidate for this mysterious HR is, I'll write it in two ways. Hopefully one of the two is familiar or convincing for you. So either this one, here I'm saying homology with coefficients in the K-theory ring spectrum of R. Never stress the fact that this is a ring spectrum, but let's not talk about this. Or equivalently, this is the smash product of your space embedded as a spectrum with KR as a spectrum. So take the one you prefer. Okay, at this point, I can actually formulate the Farrell-Jones conjecture, and then I will maybe want to pause for questions. So Farrell-Jones conjecture is actually a tentative answer to this question. So it's an answer to the question, is K-theory of a group ring somehow represented by a homology theory? But in this, it's not really represented, right? There's a classifying group in between, but in this exact way here. So Farrell-Jones conjecture, and let me say this is the version for G torsion free and R regular. There are versions, there is a version which is completely general. You just remove this to hypothesis, but it's more complicated. So let G be torsion free. Okay, let me just not write this. The so-called assembly map Hn Bg with coefficients in Kr to Kn of Rg is an isomorphism of abelian groups for every n. This is actually the first part of the conjecture. Before I give you the second one, let me say that part of the statement is that the assembly map exists, but that's not conjectural. So this thing always exists. It's not part of the conjecture. It is defined. It's not completely obvious, always defined. You have to think about it, but it's not difficult. It's not a big thing. You actually want that this is an isomorphism and this is conjectural. And the second part of the conjecture is that a similar statement, actually the same statement, basically, similar statement is true in L theory. So I will not give the same kind of introduction to L theory that I gave on K theory for time constraints. But what I can say is that, for instance, well, maybe let me say two things. So one, I don't know, remarks. One is that L theory is associated to a ring R, so just like a theory, but you also want an involution.
It seems like you're frozen and the screen disappeared.
Okay, can you hear me?
Yes, we can see your screen.
Okay, I'm sharing the wrong screen. Okay, good.
Yes, okay.
So let me say that this is can be described by classes of, this is very informal, of projective R modules, finitely generated as usual, plus a symmetric form over it, over it, them, as if of, let me say M, over it, mod what are called Lagrangians, which are actually an analog in the setting of short exit sequences. So exactly like K0 in this sense, but this is very rough. I mean, when I say symmetric, this could be replaced by other notions, so it could be quadratic or different things, and this is why usually you have a decoration here. There's variants of this, but okay, let me not delve into L theory today. But I want to stress that the Farrell-Jones conjecture really has two sides, and you always need a double statement for any kind of application, especially to the Borel conjecture. A comment here before going back to the Borel conjecture is that, so fact, this implies the two things we've been talking about before, so that reduced K0 of Zg is 0. So if this is true, in particular this is true, which was the K0 theoretic criterion for the Kaplansky conjecture, and also the weighted group of G is 0. So the second instance of this kind of phenomenon we've seen before. And all this is again for G torsion free. And finally, theorem, the Borel conjecture for G torsion free, and M of dimension greater or equal than 5 follows from Farrell-Jones. So here I mean the Borel conjecture is stated for a group and then says for every manifold. Here I'm just saying you must restrict to high dimension manifolds. Right. And for this implication, both K-theory and L-theory are needed. All right, so any questions at this point? I'm about to move to the last 30 minutes. And those will be a bit more high categorical. So if you don't like it or don't care, the talk is over. So it's a good time to stop for small questions. Otherwise, you can talk later.
This is maybe not a super relevant question, but I don't really have a good intuition for what this topologically rigid thing is. Do you have any counterexample to being topologically rigid?
Like, let me give you a non-counter example, which is the spheres. So the spheres are not spherical, but they are rigid. So of course they're not spherical because they have high homotopy group, but they're still rigid. So this doesn't work as a counterexample. Yeah, there should be plenty of. You should come up with something with, I don't know, non-trivial pi1 and pi2 maybe. This. Yeah, I don't have one on the top of my head, but maybe in the meantime I will recall something. So maybe let me get back to you at the end of the talk. Or maybe someone else has a. Yeah, but I'll keep thinking about it. Okay, so maybe I can move to the third part of the talk, which I would call Hermitian K-theory. Okay, so I will list 4 principles which are connected to one another and which will lead us to somehow a glance of how this Hermitian K-theory can help improving the Farrell-Jones conjecture. So principle 1, it's Bloomberg, Gepner, Tabuada. And it's the principle saying that K-theory can be defined as a functor from what I call cat x infinity to spectra. So this is Lurie's notation. This is the category of stable infinity categories in such a way that K-theory of the infinity category of perfect complexes on R gives you back K-theory of R. Okay. Principle 2, Lurie. Same for L theory, basically. So L theory can be defined as a functor cut infinity to spectra, and here we have a different letter, which is P, stays for Poincaré. And this is reminiscent of the fact that, as I told you before, L theory has as input not just a ring, but a ring with involution, and it's speaking about symmetric or quadratic forms. Okay, so this takes care of this whole extra thing, so this whole richness. And I'm not going to write this, but of course you want a compatibility with classical L theory. So L of perfect complexes over R with a certain structure will recover L theory of the original datum. Principle 3. This is basically Bartels, Luc, Reich. It's several works by basically these three people. Apologies if I'm forgetting someone. There's also other people, maybe less papers. Perf RG, so perf of a group ring, recall that perf is important for this reason, is the colimit in cat X of this diagram here. PG goes to cat X. Where everything just goes to perf R, both at the level of objects, there's only one object, and both also at the level of morphisms, which are non-trivial, but they all go to the identity. So let me say G goes to the, okay, maybe small g actually goes to the identity. So we are in a high homotopical world, so the colimit of this constant diagram is actually non-trivial. And it gives you back the thing you want. And the assembly map, I didn't denote it like this before, but this is the standard notation, can be realized. Sorry, maybe I should go back. As K here is this map here. So the thing you want to prove is an isomorphism in the Farrell-Jones conjecture. So what I want to say is just that SK can be realized by means of this higher categorical situation. Yeah, maybe some of you have heard that this is an application of continuous K theory. Here I'm putting something under the carpet. So our F is this diagram. In general situations, you have to rely on continuous K theory, but let me not specify this. This is just a principle, and similar for L theory. And by the way, for L theory, you don't need this continuous K theory business, in case you know what this is. Okay. Right. And the last principle, and this is in the so-called 9 authors papers. For those of you who are familiar with them, you are not familiar with it because it's part 4 and it's not online yet, but it's something. It will be online, hopefully. And maybe for those of you who don't know this, the project is called Hermitian K theory. Hermitian K theory for or of stable infinity categories. And it's a cycle of probably 5 papers, but 3 of them are online. Okay, so what's the principle contained in this paper? The left-hand side, this one. So let me remind you, you're trying to prove that this is an isomorphism. And note that this is a colimit exchange map. I've been extremely fast on this, but you may reconstruct this sentence, right? So there's a colimit outside here, and then there's a colimit inside here of the same thing. Okay. The left-hand side is not just the colimit of something, but is actually, of K theory of something, is actually the K theory of a colimit, of a lax colimit, sorry. So it's tied to the right-hand side in another way if you want. So it's K theory of a lax colimit of F. And of course, I have to give a meaning to the word lax colimit. I won't. But the point is now that you have a map between this Lux colimit in cut X and the actual colimit of the same thing, BG, and you're asking that K-theory of this thing is an isomorphism. So it's rather different than proving that the colimit exchange map is an isomorphism. You already have a map inside, and you want to prove that it becomes an isomorphism when you take K-theory. Okay, roughly speaking. And same for L theory. It's actually much easier in some sense. And what the 9 authors do in this work, they treat the case G equal to Z. And you may wonder, how is this useful? Because G equal to Z corresponds to S1 being rigid. I don't have time to explain this, but of course the consequence on the Borel conjecture is not useful because we know this very well. But there is another consequence. So this is related to what are called splitting theorems in K-theory and L theory. Okay, so actually maybe I do have time to say a couple of words about this, but let me finish before that with a statement. So this is work in the 9 authors paper. And what I mean that they treat the case, so I mean that they prove that this map here is actually the evaluation of this map is an isomorphism. So that's the wanted map as K is an isomorphism by proving something on the kernel of the map inside. Okay, let me give a name to this. Let me call this big phi. Okay. And especially in K-theory, I mean, this principle is a bit more sophisticated than what I said on the K-theoretic side, but on the L-theoretic side, it's really this. So you have a functor here. You want to prove that L-theory applied to it becomes an isomorphism. Then what you do is you look at the kernel of this functor. And you do know that under certain conditions, under certain conditions on the behavior of this kernel, L-theory will kill the kernel and will give you an isomorphism on the other two terms, because it essentially takes short exact sequences of stable categories, which have to be defined, to actual short exact sequences of spectra. Finally, all this was to arrive to the last theorem, which is work of Jordan, myself, and Victor. So what we do is, let me just say this informally first. We treat the twisted case. And this means the following. We deal with the assembly map in L theory, actually, between maybe I want to put it like this, or I don't know, okay, let me say for G equal, okay, sorry, for the ring, so where assembly map where RG, so RZ, based by R alpha Z, and maybe it's useful to remark that this RZ is just a ring of Laurent polynomials. So this is known as the ring of twisted Laurent polynomials, where alpha is an automorphism of R. So maybe some of you know the definition of this. This is R alpha. It's still the ring of Laurent polynomials, but now the multiplication is different, is twisted. So basically, if you want to multiply ax and bx, then you will get a alpha of b x squared, basically, if I remember correctly. But yeah. So it's not just ab x squared, but there's a twist. Okay. And the reason I'm saying this very informally is not just because of matters of time, is that we do prove a more abstract statement like this one. And then it's work in progress to reconnect this to an algebraic statement, to like, I don't know, L theory of this ring is splits as L theory of other components. So from the point of view of splitting theorems, there would be other descriptions. I chose to come from the point of view of the assembly maps. So we do prove that the twisted assembly map is an isomorphism, and this may or may not be relevant to you. But yeah, I guess this is what I wanted to say. Of course, in the questions, I can provide more details about this or anything else for that matter. Thanks.
Thank you very much.
Thank you.